In section 5 of chapter 13, we look at evaluating a regression equation's ability to predict. And concentration is made on two statistics, the R-squared, which is shown here in the regression output. And this is the same example that was used in previous sections relating sales goals to copiers sold. The R-squared is just the correlation coefficient squared. The correlation coefficient is R, and R-squared, as it is indicated by itself, it's R-squared. So just take the 0.865 that we obtained before as the correlation coefficient and square it. That's 0.7475. The interpretation of the R-squared is that it shows the percent variation in Y that is due to or explained by the percent variation in X. So this number is, if we multiply by 100, 76% of the variation in Y can be explained by the variation in X. And since it is R-squared, the value is always positive, and it varies between 0 and 1. As you may recall, R is a value between -1 and 1. So R-squared cannot be greater than 1. And if R is 0, then R-squared will be 0. If R is minus 0.8, R-squared will be 0.64. However, if R is plus 0.80, R-squared will be 0.64 too. So it's always positive. Now the other statistics is the standard error of the estimate. The smaller the standard error of the estimate, the higher the regression equation's ability to predict. So we need this value to be as small as possible. And as any other standard error, it is also the equivalent to a standard deviation. This value here is just the square root of the MSE. This is a mean squared error, MSE. And as you may recall from previous sections, it is the sum squares 587.11 divided by 13, the degrees of freedom of the residual. We obtain the 4516, which is a variance. The ratio of this variance to this variance gives us the F statistics, which is what we used before. So let's go back to the number 4516. That is MSE, mean square of the errors. If you take the square root of this number, you get 6.72, the standard error of the estimate. And that is the other statistics that is used besides the R-squared to measure the equations, the regression equation's ability to predict. Finally, the R-squared, going back to the R-squared, 0.7475. Remember, it shows us the percent variation in Y that is explained by the variation in X. It can also be calculated as the sum of squares due to the regression, which we called before the explained variation, divided by the total variation, in this case 2,326. So if you take 1,738.89 and divide it by 2326 or 2,326, you get 0.7475, which is the R-squared. And it is the ratio of the explained variation divided by the total variation. So we basically calculate what percent of total variation belongs to or can be attributed to the explained variation. So again, take 1738.89 divided by 2326, and that gives you the R squared 0.7475. And that is all in this section.